Yeah, I guess first I'll just show the input parameters that usually have to change when running the codes. So these green boxes show the usual ones for the input files, and then there's a small change where I also have to update these iLumo and iHomos, which are you can still get from the energy file. They're the indices that MATLAB reads for those orbitals. So, and then you also have to change IH and IE, like we've seen earlier. So those are really the only parameters you have to tune for most situations. And so that's the beginning of the file. And after having your inputs, if you scroll through, there's probably 100 lines or so of processing the Redfield tensor. So on the left shows the RRR, which would be computed from the correlation scripts. And then when this is imported into MATLAB, or for these figures, the RRR is processed into two smaller chunks. So these little bars on the right-hand side get processed into the top panel, RE, which is shown in the code. So it just extracts the information that's useful. So these little bars, and then these tall blue bars are turned into an RH file.
May I interrupt in the middle?
Yeah.
So is it possible to verbally describe what is RE and RH? Like what do they control? What they determine?
So R means red field, and then E means electron, and then H means hole. So yeah, this RH controls hole dynamics, and RE controls electron dynamics. And then, so you notice in both of these that for each bar, there's an equal and opposite bar that's with it. So that's what that technically means is for every rate that goes upward, there's the same rate that goes downward. But we know for thermal processes that downward is much more favorable than upward. So then there's another couple of lines that go through and just remove half the bars. So we only keep the downward transitions. And so then these REs and RHs on the right are what are used in the code.
May I ask?
Yeah.
So what you are telling, and I take responsibility for what is done or share it, but it means the transitions upward in energy are completely disabled. And if one would want to describe electron dynamics at high temperatures, when there is a phonon-assisted excitation, one should return them back to some extent.
Mm-hmm.
Okay, yeah, thank you.
Instead of being completely zero, just weighted by like a Boltzmann factor, or something like that.
Perfect, thank you.
And so that's the processing of the Redfield tensor. And then to make the green figures, you have to tell MATLAB to make an energy and time scale. And depending on the simulations you run, if they seem too short, so that the yellow and blue lines don't completely go to the bottom, you can increase the time of the simulation by increasing this number in the red box. That's the number I usually put, or increase or decrease, depending which way I want the simulations to go. So then, yeah, that's just setting up the grid. And then there's a couple of lines which actually do the dynamics. And I tried to link equations and the code with the boxes. So the first we have to find eigenvalues and eigenvectors, which MATLAB is specifically designed for. So finding the eigenvalues of this RE gives vectors U and then matrix elements D, which will be used to propagate the dynamics.
Can I comment? If you
Yeah, please.
So this is mostly wonderful line that comes from the MATLAB features and opportunities. Through the years, there were several collaborators trying to do the same dynamics, recoded in different programming languages, and there were several failures because this line 171 that Aaron is expressed as an equation takes much longer in regular programming languages, and it brings errors and failures all the time. So it's doable, but it's much more hard. So it's just good luck that you have this line. Please continue.
Yeah. So then, say now that we have eigenvectors, these rows, we can try to find expansion coefficients for the dynamics. So like how much each HOMO and LUMO is weighted across the trajectory. So those coefficients are this red box, which involves the eigenvector U and then projected onto the initial conditions. So the IEs and IHs, which you input earlier. So with this, there are a couple of lines for the electron, and so in this case it's the electron. So the density or psi is propagated through all the time steps in these 5 lines of code. And then once MATLAB goes through and computes the dynamics, you can plot the changes in psi by plotting this PPE. So I didn't write it here, but to generate this figure on the left, it's waterfall PPE. So that's what you write into MATLAB.
Why I don't. May I have a question?
Yeah.
Why the K is counted from 1 to 10? What's 10 here?
So K is orbital indices. So yeah, I didn't mention it. So from this step, these psi's aren't normalized. So if you stopped at the code here, the things can get bigger than 1 fairly quickly. So to ensure that everything stays normalized, that's what this little routine does. So that when you add all of the occupations together, it equals 1.
It is a mathematical, numerical procedure, and physically, it means that we intentionally want to describe situation when there is literally 1 electron in the conduction band and 1 hole in the valence band to normalize it to 1. So one particle is promoted across the gap.
Mm-hmm. And then what this waterfall figure here shows is that the initial condition is LUMO plus 9, I think. So it starts out as 1, decays to 0, but then the populations in these other LUMO states increase and then decrease until it reaches the LUMO orbital. And then the last slide I'll show is just a simple, kind of cheesy way to introduce non-radiative recombination. So in real life, this LUMO orbital should decay back down into 0 over time due to non-radiative recombination. And to implement that, I have just been multiplying these PPE populations by a single exponential decay, which comes from the HOMO-LUMO positions of the RRR file. But the main takeaway is, instead of this LUMO orbital increasing all the way to 1, it increases and then starts to decrease at some time. And yeah, that was the last slide I have.
Okay, please join me in thanking Aaron or Dr. Forde for teaching. I think it is really helpful, and it provided foundations to previous 2 presentations. And there are questions in the chat line, and maybe there will be additional questions in voice line, verbal questions. Please go ahead.
Aaron, could you please go back 2 or 3 slides before? One before, maybe another one. Oh yeah, what's the line 161? What's the E grade here from -3.5 to 4.5?
So that just, so you know, in your green figure, the y-axis is energy.
Mm-hmm.
So that's defined here. So that's,
You arrange that here.
right, so yeah, this is your range. So it's, yeah, the lowest energy you can plot is -3.5 eV, and the maximum you can plot is 4.5.
Okay, good. Thank you.
More questions? There is a question from Dr. Han to Dr. Forde. Ewan, would you like to verbalize your question?
I guess my question is why only the real part of diagonal element is kept and you ignore the imaginary part?
Slide 9, I think. So let me try. Right now we are focusing only on diagonal elements of density matrix. They are real, or they must be real. And if we inspect the result without mandating this part to be real, without this intentional cutting off imaginary part, there will be imaginary part at the level of numerical error. Something like population at given time will be 0.99999 for real part and 1 to the -15 in the imaginary. But this imaginary part, which is negligible, it just will negatively affect visual presentation. It will corrupt some figures. One can keep it here and then, but so there is a possibility to prove it numerically that imaginary part is negligible. But even this negligible part creates problems that needs to be removed. Would you buy this?
Yes.
Okay. Yeah, thank you. More questions to Aaron?
I have another one. So
Please.
in this slide, what's the meaning of enforced self-consistency?
So it ensures that at each time step, the sum of the columns is equal to 1, so that when you add all the occupations together, that it's equal to 1. Because since it's the time steps are logarithmic, are exponential. Early in the dynamics, sometimes the steps can get too large, and the populations can grow exponentially.
Yes, numerical. It's a way to fight numerical error, and here with the diagonalization method, numerical error is substantially reduced, but still present. If someone is solving equation of motion for density metrics, not by diagonalization, but standard solution of differential equations, like Runge-Kutta, errors accumulate very quickly. It is known in the community because this Redfield equation is based on perturbation theory, and perturbation theories do not conserve norm. So we intentionally do steps to conserve norm to have the realistic values of observable and observables, and it is not big achievement or big shortcoming of this method. It is quite standard situation in the community.
So here you use a value of 10. So is there anything special about this value?
No, it's empirical. It would work with maybe with 5, and it will work with 20. But if one removes these lines completely, the population will grow exponentially after maybe 400 time steps due to accumulation of numerical error. So at each step, numerical error is less than very small fraction of percent, but as if you do not correct it, norm diverges from 1, and then because of the nature of these equations in previous slide, Aaron, can you please click on slide number 8? So blue box shows the eigenstate is multiplied by e to the power eigenvalues times time. So it has exponential nature, and even small error is getting exaggerated very quickly. So these tricks to preserve normalization are justified. You want, do you accept it or?
Yes, everything's fine.
Yeah, thank you. There is a question from Kia, but the question is directly to me, not to everyone. The small k from 1 to 10, I think it is question to slide number 9. Is that small k equals 1 to 10? No. K is asking if these lines 202 to 204 related to temperature. No, I do not see direct connection to temperature. It's just error comes from the.
If I just slide number 5, you showed this slide number 5 there. So sorry, no, not slide number 5. Sorry, slide number 8. Yeah. So yes. So here
T
we use
is
k.
time. T is
Yeah,
time.
that small k is, I think, that exponential, that value.
So the values of the eigenvalue, the omegas, should be negative. And it is an interesting mathematical question to look into this eigenvalues and see if they all are negative and real. But the T is definitely time, not temperature.
Okay. So that k equal to 1 to 10, it's the eigenvalue, right?
No, K here in this slide and K in the next slide are different.
Oh, it's a difference.
K is just summation index, and it doesn't matter which letter we use.
Okay.
Thank you for asking. Any other questions?
K and k max is different.
What?
Here in the next for loop, I equal to 1 to k max. That k max is different.
Yes, K max is count of orbitals. So we should apply this normalization to each orbital to each orbital. Okay. More questions 1. More questions 2. More questions 3. So please join me in thanking Aaron